Dear students, welcome to the course of Control System Engineering offered at Electrical and Computer Engineering Department. Hope you all are doing very well and wishes good health for your family members in this pandemic of coronavirus. I am Narayan Longani, your course instructor for Control System Engineering. Dear students, starting with lecture 1, this lecture is basically about introduction to control system and the reasons why this course is included in your course outline. In real life, you may observe many physical systems which are performing their operations, and thoughts may come to your mind that what are the rules and what are the principles are being followed by these systems. Basically, you will explore what are the principles or laws and what is the equation which is being followed by these systems for their operations. Okay students, starting with CLOs or course learning objectives. As I said in previous slide that we will observe the physical systems and find out what is the principle or what is the key equation being followed by this system. This course of Control System Engineering will be covering total 5 CLOs, CLO 1 to CLO 5. Starting with CLO 1, CLO 1 deals with to develop a mathematical model for different physical systems. As I said earlier, the physical system will be following certain rule of equation. In this CLO, basically we will try to find out the mathematical model for a physical system. In this course, we will be dealing with continuous time systems and will do analysis in continuous time domain or frequency domain. In CLO 2, we will do frequency domain analysis with the help of Laplace operator, and we will develop transfer function with the help of Laplace Transform. And for time domain analysis, we will do state space modeling of the differential equation developed in CLO 1. You will be familiar with ordinary differential equation and transfer function in previous courses. Now in CLO 3, we will do time domain and steady state error analysis, and we will study these things in upcoming chapters. CLO 4 deals with stability of the system. We will find out how to check whether a system is stable or unstable. After completing CLO 1 to CLO 4, now turns CLO 5. In control system problems, there are certain set of conditions which are given. You will get familiar with these in last chapters. What are these the problem? There are certain requirements set by a user that a system must perform these functions or achieve these targets. If you have reached to the transfer function of the system from ordinary differential equation and your system is stable, then you will check whether your system is fulfilling given requirements or not. If your system is fulfilling the given requirements, then you are fine, you are done with the task, and if not, you need to design a controller to fulfill the given condition. Dear students, coming to the book affairs, we'll be using Control System Engineering by Norman S. Nice, 6th edition as our textbook, and for reference purpose you can use Modern Control Engineering by K. Ogata or any other which sounds suitable to you. Some familiar terms of this course are: your course title is Control System. This is a course of 4 credit hour. in which you will be dealing 3 credit hours for theory purpose and 1 credit hour for lab. Your course code is EE345 and prereq of this course is Signals and Systems. Moreover, students, your books Control System Engineering, Modern Control Engineering and your course outline are being uploaded on CU Online for your help. You may visit these books and course outline to study the upcoming topics for your convenience. Dear students, now coming to assessment plan. Assessment plan for online course is a bit different from the regular one. Okay, the internal marks in previous plan were divided among quizzes, assignments and sessional, where for online one, these marks are divided among 2 quizzes and 3 assignments. Okay, these are the minimum number of quizzes and minimum number of assignments. Mean minimum we have to conduct 2 quizzes and collect 3 assignments. And as earlier, final marks is again of 50%. Dear student, now we will formally start lecture 1. Starting with the contents of lecture 1, we'll start with definition of a system. We'll study what is a control system. Then further we will study what are the types of control system or how control system is implemented. Basically we have 2 types or we have 2 configuration. First one is open loop system and second one is closed loop system. We will study in detail about open loop and closed loop system and their implementation. Next we have types of input signal used throughout the course. What types of input we'll be using on various types of system. And the last one is flow diagram. That will be a flow diagram of our course. In what flow we will be moving from start to end of this course. Students, starting with system, any set of components that accept input, process it, and provides output is known as a system. Like any object, any set of component which you gave input, on application of input, system performs certain operations and provides us output is known as a system. Look at figure 1. We have a system with input R of t and output C of t. This is a simple representation of a system. You will have studied example of amplifier. Let us consider an example of an operational amplifier or a simple amplifier which gives us an amplified output. You provide an input signal of 2 volt and you receive an output signal of 6 volt. This is a simple representation of a system. Further, a system can be combination of various subsystems. If you see figure B, where a system consists of 3 subsystems and input is R of t again and C of t is output. For this you can consider an example of a robot which is an electromechanical system which consists of some electrical parts and some mechanical parts. In mechanical parts, it has driving part which performs some movements, and electrical part is that we have actuating circuit. So a system can be a combination of various subsystems. In upcoming slides you will see an example of a robot where you can clearly see it consists of mechanical parts and electrical parts. Students, now coming to control system. Control system is simply defined as applying a desired input to a system and obtaining a desired output from a system. For this purpose, the desired output or required output is applied as a desired input to a system, to which system response and system output reaches the desired level. If you see a figure which is the output graph of a system where a step input is applied, and as we know that step has an amplitude of 1 and step response must reaches the value of 1. If you see the graph, the output C of t starts from 0 and reaches to the final value of 1. So in this scenario, desired input is applied, which is step input, and desired output is obtained, which is a step output. So this is an example of control system. Okay students, now coming to some basic parts or components which we'll be using throughout the course. First one is plant, second is sensor, and third is controller. Basically these all are systems which accept input, process it, and give us output. Starting from a plant is a system which we want to be controlled or from which we want desired output. Second one is sensor. Sensor is actually used to measure the output and to monitor whether our system is moving to desired output or not. Last one is controller. Okay, controller is a basic component which provide desired signal to the plant for desired output. Now coming to configuration of control system. A control structure is implemented in two ways. First one is open loop system and second one is closed loop systems. Open loop systems. Open loop systems are a type of systems in which output is not monitored by the system. If you see the diagram, you have an input, controller, control signal, process or plant, and output. It means the system has a predefined operation against any input. You apply the input, controller process it, generate a control signal, and give it to the plant, and plant or a process generates the required output. In this type of system, output isn't feedback to the controller or is not monitored with the help of sensor. So we are not sure that whether our system is following the desired output or not. Next we have closed loop systems. These are the systems in which we monitor the output with the help of sensors or measuring element. These are the systems in which output is measured with the help of sensor or transducer or any measuring element and feedback to the system. Before controller, an error is generated between desired input and output of the system, and then according to the error, a control signal is generated by controller, and this control signal is applied to the process or plant. If this error is increasing, which means the difference between desired input and system's output is also increasing, so a closed loop system is not performing as per requirement. And if this error is approaching to zero, which means that your system output is also approaching to the desired output. Let us have a few examples of open loop and closed loop system, starting with an example of washing machine. For cleaning of clothes with detergent, water and clothes, we just rotate the knob and wait for clothes to be clean. When the time is up, we check the clothes whether the clothes are clean or not. This is an example of open loop implementation, that whether our clothes are clean or not using washing machine. What if we add a few sensors in the washing machine that will monitor or measure the level of cleanliness? And machine will be running till that desired level is achieved or not. So now after this will become a closed loop system, which will make sure that required level of cleanliness is achieved. Under this topic, next example we have is of a moving car. Consider a conventional car which is without cruise control or speed control system. In a conventional car, for desired speed to be maintained, we press accelerometer and monitor the speedometer. Now, if we want to move the car at 30 km per hour, as per requirement, we press accelerometer and cars reaches the desired speed. And after this, we maintain the same pressure on the accelerometer. Now if after the distance of 10 to 15 km, car reaches an uphill road, as the same pressure is maintained and now car is moving on an uphill road, so automatically its speed will be slowed down, but it is required to maintain the speed of 30 km per hour. But in actual, car will be moving with a speed lower than 30 km per hour. And if the car reaches to the downhill and with the same pressure on accelerometer, the car will move with speed greater than 30 km per hour, because we don't have a cruise control system which will be monitoring the speed of the car. Now we have a car with cruise control system. Now we set a desired speed of 30 km per hour. Now if we have a plain road, uphill or downhill, the cruise control will automatically adjust the speed of a car to 30 km per hour. So now this will become a closed loop system. Okay, now we will study comparison of open loop systems and closed loop systems. As studied earlier, open loop system don't have feedback path where closed loop system monitor the output of the system, which means open loop system have predefined operation. In comparison of these both configurations of system, first one is stability. As said, open loop system have predefined operation, so for any specific input, open loop system will perform respective operation. And for closed loop system, you have to determine whether your system is stable or not. In moving a system from open loop to closed loop, there exists a possibility that a stable open loop system may be transformed into unstable closed loop system. So every time in this conversion we have to determine the stability of closed loop system. Further about this we will discuss in the chapter of stability. Now second one is memory. As we know that in closed loop, output is determined with the help of sensors or any measuring element and requires comparison. For this, some memory elements may be required to store the information. Where in open loop system, you have input applied to the system and you get output. Where in closed loop system, you require comparison. For this, you may require memory elements. Last one is external disturbance. In open loop systems, there exists possibility that some unwanted signals may get added to the system and affect the performance of system. Where closed loop system show robustness towards unwanted external signals which are disturbance signals. In detail about this disturbance signal we will study in chapter of steady state error. Students, now we will study the course flow. In this course, whatever problem is given to you, you will start from mathematical modeling and try to find out differential equation of the system. Now, if we are analyzing our system in frequency domain, then with the help of Laplace operator, we will find out transfer function of the system. And if we are studying time domain analysis, then we will find state space model of the system. After transfer function or state space model, we will compute stability of the system and find out that our system is stable or unstable. If our system is stable, then we will find out time response specifications, which include transient analysis. And after transient analysis, we will study steady state error specification of this response. After step 1 to 5, we will check that whether our system is fulfilling given set of conditions or not. If time response specification meet the given set of requirement, then we are done here. And if certain changes are required, then we'll have to design a controller for a system. And also, if our system is unstable, then we have to design a controller for this system. This is the whole flow of the course, how we'll start from mathematical modeling, transfer function, state space, stability, time response, steady state error, and at the end we'll design controller for a system. Students, now we'll study various test signals which we'll use throughout this course. These signals will be applied to a system and certain time response specification and steady state error specification will be checked. Many of you will be quite familiar with these input signals. In the series of input signal, first one is impulse signal. Impulse have an area of 1 and graphical and mathematical form are given in this table. This signal is used for testing transient response modeling. Second one is step signal. Step signal is represented by u of t and its magnitude is equal to 0 for time less than 0 and magnitudes equal to 1 for time greater or equal to 1. And this signal is used for transient and steady state error modeling. Third one is ramp signal. Ramp signal is basically integrating a step signal. Its mathematical model and graphical representation is given here. Ramp signal response also exists for time greater or equal to 0 and for time t less than 0 its response is equal to 0. In this sequence, third signal is parabola signal, which is used for steady state error analysis. Parabola signal is like integrating the ramp signal. Last we have is a sinusoid, which is used for transient modeling and steady state error modeling. Mathematical form is given in the table. Now if any of you have any questions, please ask. Dear students, welcome to the second online class of Control System Engineering. In first lecture, we studied about Introduction to Control System, what is control system, and course learning objectives. Then we studied about book to be followed and assessment plans. Then formally we start with the definition of a system, control system, and types of configuration. Any object that accepts input, process it, and give us an output is known as a system. And to obtain desired output from a system, we apply desired input. This is known as control system. And then we studied about controller, plant, and a sensor. Any system whose output is going to be controlled will be known as a plant. Its output will be measured by a sensor, and its output will be controlled with the help of a controller. Then we studied about configurations of control structure. First one is open loop system and second is closed loop system. The basic difference between open loop and closed loop is feedback path. In open loop systems, we don't have feedback path and have a predefined input-output relation. Where in closed loop system, we have a feedback path and we monitor the system's output with the help of an error. Then we studied few examples of open loop systems and closed loop systems. Then we made a comparison of open loop and closed loop systems, and after this we studied the course flow. If we are given a desired task, we'll start from mathematical modeling, transfer function, stability, time response specification, steady state error, and then control the design. After this, we studied test signals. And this was an overview of online lecture. Dear students, control theory is divided in two domains. If we are studying classical control, then we will be analyzing a system in frequency domain, and if we are studying modern control, then we will be analyzing a system in time domain. Our second chapter is titled as Modeling in Frequency Domain. In this chapter, you will study about Laplace transform, inverse Laplace, how to take Laplace transform of nth order differential equation, and to find out transfer function of the system. Then we'll study various linear time invariant electrical, translational mechanical, rotational mechanical, system with gears, and electromechanical system for their transfer function. Then we'll study about analogous behavior of electrical and mechanical system, and we'll get familiar with nonlinearities, and we'll study about linearization. Dear students, in lecture 2, we'll study about Laplace transform, definition, transform tables, transform theorems, how to find transfer function of nth order systems, and inverse Laplace. After Laplace transform, we'll study electrical network transfer function. In this, we'll find out transfer function of simple electrical circuits. Dear students, now starting with Laplace transform. As you studied in previous courses, Laplace transform of function f of t is an integral multiplied by exponential power e power minus st, where s is Laplace operator and is equal to sigma plus j omega. Graphically, S-plane is represented as a two-dimensional plane where one axis is sigma and another axis is j omega. For this integration, the function f of t must be integrable and must not be discontinuous at any time. Students, now we will study with the help of an example to find out Laplace transform of a function f of t, where f of t is equal to capital A exponential e power minus at u of t. This function is product of constant capital A, exponential function, and a step function, which implies that for time less than 0, function results 0. Now to find Laplace transform, we'll use definition as studied in previous slide. Now using property of integration for exponential function, we come to result that Laplace transform of function f of t will be equal to capital F of s will be equals capital A divided by s plus small a. Now if we see time domain relation, the small a was present as a power of exponential term, where in Laplace domain relation this is present in denominator of the function. In last class, we have studied about various text signals which we are going to use throughout this course. And as we are studying frequency domain, So we will study Laplace transform of these test signals. These are the relations which we are going to use throughout this course for conversion between time domain and frequency domain. For delta or impulse, we have Laplace transform of 1, for step 1 over s, for ramp 1 over s square, and so on. Similarly, for parabola can be found with relation given in item number 4, and similarly Laplace transform can be found for sinusoid given in item number 6 and 7. Students, now we will study various theorems which will provide conversion of time domain to frequency domain relations. This table includes definition of conversion, linearity theorem, frequency shift theorem, time shift theorem, scaling theorem, theorem used to find Laplace transform of first order derivative, second order derivative, and nth order derivative. Among these three, it's important to note down that after conversion from time domain to frequency domain, initial conditions are also a part of frequency domain relation. Next is integration theorem, final value theorem, and initial value theorem. Now we'll study how to find transfer function of nth order system with the help of Laplace transform. For this, consider a linear time invariant system whose input is represented by r of t and output is represented by c of t. The nth order differential equation of this linear time invariant system is represented here. This equation also contains constants a naught to an and b naught to bm. Now for transfer function, we will take Laplace transform with the help of theorem studied in previous slide, and we'll come to an equation involving constants a naught to an, b naught to bm, Laplace operator s, and output represented by capital C of s and input variable represented by capital R of s, and initial conditions associated with input R of t and initial condition associated with output C of t. Further, we'll assume that all initial conditions are 0. This means that system is initially at rest, or we don't have any prior information of the system. After Laplace transform, our time domain equation is converted into simple algebraic equation, and after setting initial conditions equal to 0, we can simply take variable C of s common from all the terms involving it, and similarly R of s common from all the terms involving this. Now, using cross multiplication, we will reach to desired transfer function C of s over R of s, which will be also represented by G of s. Okay, last we have a block representation of the transfer function. In previous slide, we were having a system with input R of t, output C of t. Now this is represented by, in Laplace domain as, a block diagram with input R of s, output C of s, and system is represented by transfer function g of s, whose numerator has highest power of m and denominator had highest power of n. So this is our transfer function for nth order linear time invariant system. Now to make things more clear, look at example. In this we have a first order input-output differential equation of a linear time invariant system, and we have to find transfer function. For this transfer function, first of all, we'll take Laplace domain transform with initial conditions equal to 0, which give us equation 2.56. Now this equation is simple algebraic equation where we can take variable common. You can take c of s common from terms involving sc of s and 2c of s. With this you will come up to s plus 2 whole multiplied by c of s, and equation will be equal to r of s. Now again using cross multiplication, you will reach to transfer function g of s, which is equal to c of s over r of s, and this will equal to 1 divided by s plus 2, and this will be transfer function of our linear time. Last topic under the series of Laplace transform is inverse Laplace. With the help of relationship given here, you will find out time domain function f of t from Laplace domain function f of s. But throughout this course, we will be using Laplace table and Laplace theorem studied in previous slides for conversion between time domain and frequency or Laplace domain. Now look at an example. In this example, we have a system g of s whose transfer function is given by 1 divided by s plus 2. The input applied to this system is step and is represented by variable r of t in time domain and capital R of s in Laplace domain. We have to find time response of this transfer function. For this, as we know that step input is represented by 1 over s in Laplace domain, and output of the system is equal to input r of s multiplied by g of s in Laplace domain. Now for time response, we will check the relation of c of s may look familiar with any of relation from Laplace theorem table or Laplace input signal transform table. But unfortunately, we won't find any relevant form. So for this, we'll use partial fraction and convert relation of c of s into any appropriate form from that table. So after partial fraction, we have reached to equation half multiplied by 1 over s minus half multiplied by 1 over s plus 2. Now if you look at slide number 7, in which we have studied Laplace transform of various input signal, and these both terms get some familiar form. Now we will apply inverse Laplace on whole equation of c of s And then with the help of linearity theorem, we'll apply inverse Laplace on each individual term. Then using Laplace transform table for various signals, we'll get time domain response C of t. And this is all about Laplace. Dear students, so far we have studied Laplace transform, which we will be using to find out transfer function of various systems. In the series of systems, we'll start from electrical network transfer function. Under this topic, we'll find out transfer function of various electrical network. And these networks include networks associated with resistor, capacitor, inductor, and we will also find transfer functions of operational amplifier circuits, which includes inverting amplifiers and non-inverting amplifiers. Before starting electrical networks associated with passive linear components, let us study what are these passive linear components. These components include capacitor, resistor, and inductor. If you look at the table, the first column specify voltage current relation for capacitor, resistor, and inductor. The second column specify current voltage relation for capacitor, resistor, inductor. The third column specify voltage charge relation for capacitor, resistor, inductor. The fourth column gave us impedance relation for capacitor, resistor, inductor in Laplace domain. And the last column gave us admittance, which is opposite of impedance for capacitor, resistor, and inductor in Laplace domain. Now we will start simple circuits for electrical network transfer function, which is an RLC network. If you look at the figure, in this we have inductor, resistor, and capacitor connected in series, and source voltage is V of t, and current moving through the circuit is I of t. And we have to find out transfer function relating capacitor voltage Vc of t to input voltage V of t in Laplace domain. The first step in finding out transfer function is to convert impedance of inductor, resistor, and capacitor from time domain to Laplace domain using the table studied in previous slides. Similarly, the voltage source V of t and the current moving through the circuit will also be transformed in Laplace domain. Now you have studied a number of methods in the course of electric circuit analysis through which you can find transfer function Vc of s over V of s. We'll start from single loop differential equation method. For this method, we'll apply KVL at circuit. Now KVL will give us first equation, which states that sum of voltage across inductor, resistor, and capacitor will be equal to the source voltage. Now we'll replace voltage across inductor, resistor, and capacitor with its voltage current relation given in table at slide number 15. Now as we know that current is equal to the rate of change of charge, now replacing the current in the second equation will give us second order differential equation, and as we know that charge across capacitor is equal to capacitance of capacitor multiplied by voltage of capacitor. Now again substituting this, we'll have a second order equation whose variable are capacitor voltage and source voltage, where resistance, capacitance and inductance are constant. Now we'll take Laplace transform with zero initial conditions to find out transfer function. With Laplace transform, our time domain equation will be converted into simple algebraic equation. Now by simply taking Vc of s common and using cross multiplication, we can have our desired transfer function Vc of s over V of s. And we can analyze this system using a block diagram representation where input is V of s and output is Vc of s. Another method we can use is single loop transform method, in which we use Ohm's law, which implies that voltage will be equal to current with the product of impedance. Now from previous method we have applied KVL and reached to first order differential equation where variable terms are current and voltage. Now if we take Laplace transform with zero initial condition, we'll have a simple algebraic equation. Now using cross multiplication, we'll have a transfer function of current to source voltage, and on further simplification we can have a relation for current I of s. Now using the voltage current relation studied earlier, we have that in Laplace domain, voltage across capacitor is product of current through the capacitor and impedance of capacitor, which is 1 over Cs. Now simply replacing the current and few rearrangement will give us our desired transfer function Vc of s over V of s, which is same as in previous case. Next method in this series is voltage division rule. With voltage division, we can simply find voltage across capacitor, which states that the component across which you are finding the voltage will be equal to impedance of that component divided by total impedance of the circuit, and this whole term will be multiplied by the source voltage. Now again doing cross multiplication, you will get transfer function Vc of s over V of s. Dear students, the last method, single node through transform methods, through which we will find our desired transfer function Vc of s over V of s. For this we assume that we have a node Vc of s. The current entering the node is equal to potential difference between the nodes divided by impedance, which is Vc of s minus V of s divided by impedance of resistor and inductor. Now current leaving through the node will be equal to Vc of S divided by impedance of capacitor, which is 1 over Cs. Now with the help of KCL, we'll obtain equation of the circuit, and then further solving with simple rearrangement, we'll obtain our desired transfer function. Now if any of you have any questions, please ask. Dear students, welcome to the third online class of Control System Engineering. In previous class, we started with classical and modern control. Then we studied outcome of this chapter, what you are going to learn after this chapter. Then we started with Laplace transform. We studied the definition of Laplace transform. Then we studied a Laplace transform table in which we studied about various test signals which we are going to use in this course, their time domain and frequency domain representation. Then we studied Laplace transform theorems, various theorems which we are going to use throughout this chapter. And then we studied a method through which we can find transfer function of nth order linear time invariant system. And we concluded Laplace transform with its final topic of inverse Laplace. After this, we started electrical networks. We get familiar with the components which we are going to use throughout this course, which includes capacitor, resistor, and an inductor. Then we studied a simple RLC based network, and through various methods we find out transfer function Vc of S over V of S. With any method you are going to start, it's important that you must transform impedances from time domain to Laplace domain, and similarly transform voltage sources and current sources to Laplace domain. So far in chapter 2, which is modeling in frequency domain, we have studied about Laplace transform, inverse Laplace, transfer function of differential equation, and how to find transfer function. We have started electrical network transfer function, which we are going to conclude in this chapter. And the remaining topics of this chapter will be covered in upcoming online lectures. Contents of this lecture are impedance of electrical components, electrical network transfer function for complex circuits, and method includes mesh analysis and nodal analysis. Next topic is impedance for electrical components. If we look at a portion of table studied in previous lecture, which gave us voltage current relation for capacitor, resistor, and inductor. And now if we take Laplace transform for voltage current relation of capacitor, which is V of t is equal to 1 over capacitance of capacitor multiplied by integral of current passing through the capacitor. After Laplace transform, voltage across capacitor will be equal to 1 over Cs, which is impedance of capacitor multiplied by current through the capacitor I of S. Now for resistor, V of t is equal to resistance of resistor R multiplied by current flowing through resistor, which is I of t. In Laplace domain, this equation will be turned into V of S is equal to R multiplied by I of S. Now for inductor, we know that V of t is equal to inductance of inductor multiplied by rate of change of current passing through it. In Laplace domain, voltage equation will be V of S will be equal to Laplace operator S multiplied by inductance of inductor multiplied by current flowing through inductor. If we analyze both three equations, we'll see that voltage across capacitor, resistor or inductor is equal to impedance of respective component multiplied by current passing through the component, or impedance is equal to voltage of the component divided by current passing through the component. So Z of S is equal to V of S over I of S. Or we can say that sum of applied voltages is product of sum of impedances multiplied by current passing through these components. Dear students, now we will start analysis of complex circuit with the help of mesh method. In this, we may have two or more loop circuits for which we are going to find respective transfer function. For mesh analysis, we have certain rules which we are going to follow. The first rule is replace passive element values with their impedances. Second one is transform voltage sources or current sources from time domain to frequency domain or Laplace domain. Third rule is to define direction of current in each mesh. After defining the current direction, we will apply Kirchhoff voltage law around each mesh, and we'll assume that current of mesh or loop on which we are going to apply KVL is higher than all other currents of the network. After step 4, we'll have a simultaneous equation for the system, and we'll solve this equation to find the transfer function of the system. Dear students, now we will study with the help of example how to apply mesh analysis. In the given example, we have to find transfer function I2 of S over V of S, and the given circuit is two loop electrical network circuit. In mesh 1, we have a voltage source V of t, resistance R1. In mesh 2, we have resistance R2, capacitor C, and in between both mesh we have an inductor. Now we'll start the analysis by first step, which says that transform the impedances from time domain to frequency domain. Both resistors R1 and R2 will be written same as they were in time domain. Impedance of capacitor will be 1 over Cs, where impedance of inductor will be Ls. The voltage source in mesh 1 was V of t, and it will be transformed into V of s, where current of mesh 1 was small I1 of t, and it will be transformed into capital I1 of s. The current of mesh 2 is small I2 of t, and it will be transformed into capital I2 of s. With this we have covered two rules of the analysis. Now for rule 3, which is to define the direction of current, we'll define a clockwise direction of current I1 of t and similar direction. Now we'll apply fourth rule of analysis, which is to apply KVL around each mesh. And assuming that current of each mesh which we are going to analyze is higher than all other currents of the network. And with this we'll have first equation of the system. Now we'll apply KVL across second mesh and we'll obtain second equation of the system. As this is a two loop system or two mesh system, we'll require to find out two equations which will completely define the behavior of voltage and current across this electrical network. After some arrangements in these equations, we will get this desired form. Now you have liberty, or it depends on you, that what rule you are going to use to find out transfer function, whether it is Cramer rule, whether it's substitution method, echelon method, or reduced echelon method, or matrix inversion method. This selecting of rule will be your choice. We are here using Cramer's rule, which defines that I2 of s will be equal to del 2 over del, where del 2 is defined as a numerator and del is defined in next slide. In previous slide we have found the value of del 2, which is equal to Ls multiplied by V of s, and now we'll find the determinant of value of del and substitute in the equation of I2 of s, and making some rearrangement we'll get our desired transfer function, which is I2 of s over V of s. This transfer function can also be represented in block diagram form, whose input is V of s and output is I2 of s, where system transfer function is represented by G of s. Dear students, now if we analyze set of equations obtained in previous examples, we conclude that for mesh 1, impedance R1 is present, voltage source is present, and impedance of inductor is common between both meshes. Now its equation is turned out to be R1 plus Ls multiplied by I1 of S minus impedance of inductor multiplied by current is equal to V of S. And for second mesh, we observe that capacitor and resistor R2 are present in second mesh, and again impedance of inductor occurs common between both meshes. Now the generic form will be somewhat like sum of impedance present around mesh 1 multiplied by current of the mesh I1 minus sum of impedances common to the two meshes, in this case was inductor, multiplied by I2 of S will be equal to sum of applied voltages around mesh 1. Similarly for second mesh, equation will turns out to be sum of impedances around mesh 2 multiplied by current of mesh 2, which is I2, minus sum of impedances common to the both meshes multiplied by I1 of S will be equal to sum of applied voltages around mesh 2. This will be our generic form and will be used in inspection method to find out equation of system for two-loop electrical network. Dear students, next topic we are going to study is complex circuit analysis with the help of nodal analysis. Like mesh analysis, here again we have certain set of rules which we are going to follow to solve a circuit. First rule is to replace passive element values with their admittance. Second rule is to replace all sources and time variable with their Laplace transform. Third rule is replace transform voltage sources with transform current sources. After rule 3, we'll apply Kirchhoff's current's law at each node. After KCL, we'll obtain set of simultaneous equation and we'll find out transfer function by solving these set of equations. Dear students, now we will apply nodal analysis in an example. In this example, we'll find transfer function Vc of S over V of S with the help of nodal analysis. Like previous one, first step was to find impedances of each element. In case of nodal analysis, we'll find admittance of each component present in this circuit. In case of resistance, we'll be using conductance, which is represented or equal to 1 over resistance. Conductance is represented by G and equal to 1 over R. Before applying nodal analysis, we'll assume that at node at which we are going to apply nodal analysis is at higher potential than all other nodes. We'll apply nodal analysis at node V of S and obtain first equation of the system, and then we'll apply nodal analysis at node Vc of s to obtain second equation of the system. We'll use these both equations to find required transfer function. Now with certain rearrangement, we'll replace resistance by conductance, and both have inverse relation. And after this, we obtain two equations for this system. Now again, this is a choice of student which method he is going to follow, and with this we'll obtain transfer function Vc of s over V of s, which is our required transfer function. And in block diagram form we have a system with transfer function Vc of s over V of s, whose input is V of s and output is capacitor voltage. Dear students, now look at the next example. In this example, same circuit is used, but the voltage source is transformed into a current source using source transformation. Now, if you look at figure 2.8, which is a transform network ready for nodal analysis. In this, V of s multiplied by G of s is the current source. VL of s is a node where current is getting divided. And Vc of s is our second node. First we will apply nodal analysis or Kirchhoff current law at node VL of s and obtain first equation for this system. Then we'll apply nodal analysis or KCL at second node Vc of s and obtain second equation for this system. Now we'll solve both these equations to obtain our required transfer function, which is Vc of s over V of s. Dear students, now we'll try to find some generalized form for inspection method. Given equations obtained from previous examples, if we observe these equations, we conclude that at equation of node 1 is formed by all the admittance connected directly to the node 1 multiplied by node 1 voltage, which is VL of s, minus admittance which is common between node 1 and node 2 multiplied by second node voltage will be equal to the sum of applied current at node 1, which is V of s multiplied by G1 of s. Similarly, for second node, the equation will be all the admittance connected direct to the node 2, which is G2 of s plus C of s multiplied by the node voltage and subtracting admittance of component which is common between node 1 and node 2, or node Vc of s or VL of s, that is G2 of s, and will be equal to sum of applied current at node 2. And hence this will be our generalized form for nodal analysis. Dear students, in next example we are going to do mesh analysis for a system with 3 loops. The rules are same as said earlier. First of all, we'll replace all the passive elements with their impedances. In second rule, we'll replace all the sources and time variable with Laplace transform. For rule 3, we'll assume a transform current and define the direction of current in each mesh. For rule 4, we'll apply the KVL at each mesh and assume that loop at which we are applying KVL has high valued current compared to all other currents of the network. And with this, we'll obtain a set of simultaneous equation for a system and we will solve as per requirements. Now we'll study a generalized form for inspection method for a 3-loop electrical network. For loop 1, equation will be sum of all the impedances around mesh 1 multiply by mesh 1 current, subtracting all the impedances which are common between mesh 1 and mesh 2 multiplied by the mesh 2 current, subtracting all the impedances which are common between mesh 1 and mesh 3 multiplied by mesh 3 current, and this will be equal to sum of applied voltages around mesh 1. For second mesh or equation will be sum of all the impedances around mesh 2 multiplied by second mesh current minus sum of all the impedances common between mesh 1 and mesh 2 multiplied by I1 of S minus sum of all the impedances common between mesh 2 and mesh 3 multiplied by third mesh current, which is I3 of S. And this equation will be equal to sum of applied voltages or any voltage source present at mesh 2. Now for mesh 3, equation will be like sum of all the impedances present at mesh 3 multiplied by mesh 3 current, which is I3 of S, minus sum of all the impedances common between mesh 2 and mesh 3 multiplied by second mesh current, which is I2 of S, and minus sum of all the impedances common to mesh 1 and mesh 3 multiplied by first mesh current, which is I1 of S. And this will be equal to sum of applied voltages or any voltage source present at mesh 3. This will be our generalized form, and with this we'll find equation of system. Any system now, using generalized form studied in previous slide, we'll find out 3 simultaneous equations for this electrical network, and this equation will define behavior of currents and voltage across any component present in this electrical network. Now, if any of you have any questions, please ask. Dear students, welcome back to the class. This is our fourth lecture of Control System Engineering. In previous class, we studied about impedance for electrical components, electric network transfer function for complex circuits. The method we used were mesh analysis and nodal analysis. In impedance for electrical component section, we observe that voltage across any component is equal to impedance of that respective component and current flowing through the circuit. Then we started mesh analysis for complex circuits, which was based on certain set of rules. After this, we studied a generalized form for inspection method. Then we studied nodal analysis, which can be applied to any two-node circuit by following given rules. Then we studied a generalized form for inspection method. At last, we studied a three-loop electrical network and analyzed the equation with the help of inspection method. Dear students, till now in this chapter of modeling in frequency domain, we have covered Laplace transform, inverse Laplace, finding transfer function from differential equation, and electrical network components and their circuits. After this lecture, you will be able to find transfer function for various type of electrical networks. And remaining topics will be covered in upcoming lectures. In this lecture, we will study about operational amplifier and their configuration. Basically, we will study two types of configuration. First one is inverting operational amplifiers and second one is non-inverting operational amplifier. After this, we will start translational mechanical system. We will get introduction to the components used under this topic and we'll try to find transfer function for simple systems. Dear students, now we'll start our operational amplifiers. I will give you a just brief overview of operational amplifiers. Operational amplifier is an electronic amplifier used as a building block to implement transfer function. If you look at the figure of operational amplifier, it specifies that it has two input V1 of t and V2 of t. Output is V0 of t. A is the gain of the amplifier. V plus and V negative are the actuating voltage of this amplifier. Operational amplifier has few characteristics. It has a differential input which is equal to V2 of t minus V1 of t. It has high input impedance. Ideally, this is equal to infinity. A very low output impedance, ideally which is also equivalent to 0, and a high constant gain of amplification A, which is also equal to infinity in ideal case. The output of operational amplifier is given by gain of the amplifier A and differential input V2 of t minus V1 of t. Dear students, We will study two configurations of operational amplifier. One is inverting operational amplifier and second one is non-inverting operational amplifier. We'll start from inverting operational amplifier. In inverting operational amplifier, one of the input of op-amp is grounded. If you see the figure, the second input V2 of T of operational amplifier is grounded and its output relation is equal to gain of the operational amplifier A with a negative sign multiplied by V1 of T, which implies that in this case our output is out of phase with respect to input. Dear students, now we'll study how to find transfer function for inverting operational amplifier. Now if you look at the figure where input is given by Vi of S, input impedance is represented by Z1 of S and I1 of S is input current. V0 is the output of the system and Z2 of S is impedance of feedback path, where feedback path current is represented by I2 of S. Now we'll use the characteristic which states that op-amp have high input impedance and ideally it is equal to infinity. And we know that current always follow the path which have minimum impedance. So IA of S will be equal to 0, which implies that V1 of S is also equal to 0 as no current is flowing, so there is no potential difference. Now input current I1 of S will be equal to input voltage divided by input impedance. The feedback path current I2 of S will be equal to output voltage divided by impedance of feedback path, which is Z2 of S. Now we will apply nodal analysis at node V1 of S. Now the current entering the nodes are I1 of S and I2 of S, where current leaving the node is IA of S, which is also equal to 0. So I1 of S will be equal to minus I2 of S, and on substituting values of I1 of S and I2 of S, we'll get relation input voltage Vi of S divided by input impedance Z1 of S will be equal to minus output voltage V0 of S divided by feedback path impedance Z2 of S. Now rearranging these variables will give us our desired transfer function, which is V0 of S over Vi of S will be equal to Z2 of S over Z1 of S. In this, Z2 of S is impedance of feedback path, where Z1 of S is impedance of input path. Dear students, now with the help of example, we'll get inverting amplifier more clear. In this example, you have to find a transfer function V0 of S over Vi of S for the circuit given in the figure. Now if you look at the input path, the input impedance consists of two components, a capacitor and a resistor. Similarly, the feedback path also have two components, a resistor R2 and a capacitor C2. So before solving, we have to find equivalent impedances, and for this we'll replace passive components with their equivalent impedance in Laplace domain. After conversion into Laplace domain, we'll find equivalent impedance. The components present in the input path are in parallel combination, where the components present in the feedback path are in series combination. Now using relations for parallel and series circuits, we'll find the equivalent impedance Z1 of S and Z2 of S. And then we'll substitute these values in our desired transfer function, which is V0 over Vi of S is equal to minus Z2 of S divided by Z1 of S. Students, the second configuration we are going to study is non-inverting operational amplifier. In this case, your output is in phase with input. Now, if you look at the figure of non-inverting operational amplifier, none of the input is grounded directly, as it was in the case of inverting operational amplifiers. And its transfer function is equal to Z1 of S plus Z2 of S whole divided by Z1 of S. Dear students, now we'll study how to find transfer function for a non-inverting operational amplifier. Given we have a figure whose output is V0 of S and the external input Vi of S is applied to second input of operational amplifier. If we look at the feedback path, it starts from V0 of S and it has two impedances Z2 of S and Z1 of S, and then it is grounded. Now V1 of S is a voltage across Z1 of S is applied as a second input to operational amplifier. Now we know that output of operational amplifier is given by gain of operational amplifier A multiplied by the differential input, which is V2 of t minus V1 of t. Now if we apply voltage divider rule in feedback path to find out voltage V1 of S, we will get V1 of S will be equal to Z1 of S divided by impedance of the feedback path, which is Z1 of S plus Z2 of S, and this whole term multiplied by the source voltage, and in this case loop starts from V0 of S and going through Z2 of S, Z1 of S, and then grounded. So V0 of S act as a voltage source here. So this whole term will be multiplied by V0 of S. Now substituting the value of V1 of S in the difference part of output equation, we obtain a relation of V0 of t, which is equal to gain multiplied by difference of input voltage with V1 of S, which has a predefined relation. Now we will do certain rearrangements to find transfer function when V0 of S over Vi of S. Students, now we have obtained a relation for V0 over Vi of S, but as we know that gain of op-amp is quite high and is ideally equal to infinity. So 1 present in the denominator term is quite negligible compared to the gain of op-amp. So we'll neglect here and we'll obtain our desired transfer function, which is Z1 of S plus Z2 of S over Z1 of S. Students, now we'll discuss an example for non-inverting operational amplifier. In this example, we have to find transfer function V0 of S over Vi of S. The first step in this solution will be transform or replace the passive elements with their impedance in S domain. And then we will use transfer function from last slide. Again, if you look impedance Z1 of S and Z2 of S, Z1 consists of two components connected in a series form, where Z2 of S consists of two components connected in parallel form. So by using desired relations for series and parallel form for impedances, we'll find our desired transfer function, which is V0 of S over Vi of S. And this is all about transfer function for electrical networks. Now we'll start some mechanical systems. Dear students, we have completed transfer function for electrical networks. Now we'll start translational mechanical system and we will study how to find transfer function for them. In this case, we'll again study passive linear components used in translational mechanical system. The first component is a spring, which is the energy storage element. Second one is mass, which is again an energy storage element, and the last one is viscous damper, which is a energy dissipating element. We'll be using these three components in our upcoming topic. Dear students, before starting translational mechanical system analysis, let us study force velocity relation for a spring, viscous damper, and mass. Similarly, force displacement relation for a spring, viscous damper, and mass, and their impedances for spring, damper, and mass. Dear students, now we will study simple translational mechanical systems. To find out transfer function of these systems, we have a few rules to be followed. First of all, we have to define equations of motion. In case of simple translational mechanical system, one equation is required to define the motion of the system. Second step is to draw a free body diagram. In third step, we define direction of motion on free body diagram. After defining the direction of motion, in next step, we will place all the forces acting on the body, either in the direction of motion or opposite to it. And then with the help of Newton's law, we will form a differential equation and sum it to 0. And then using Laplace transform, we will separate the variables and will reach to our desired transfer function. Dear students, now we will study an example in which we will find a transfer function for a simple translational mechanical system, which is x of s over f of s. To solve this, we'll start from number of equations. As we know that this is a simple translational mechanical system, so a single equation will be required to define its dynamics. In second step, we'll draw a free body diagram. Then we'll define direction of motion, and then we'll place all the forces acting on the mass either in the direction of motion or opposite to the direction of motion. Then with the help of Newton's law, we'll find differential equation of the system, and then with the help of Laplace transform, we'll find our desired transfer function. If you look at the free body diagram given in figure A, it states that the object M or mass M is moving towards right, which is the direction of externally applied force. Now we'll place forces acting on the mass M due to components attached to it. The components attached to mass M are a spring and a damper. Now spring will resist its motion and apply a force opposite to the direction of motion, which will be kx of t. Similarly, the viscous damper will also oppose its motion in the direction of x, so it will apply a force opposite to the direction of motion. And lastly, its inertia will also oppose its motion. So these three forces will act in the direction opposite to the x of t, where only force f of t will act in the direction of x of t. The figure P gave us forces acting on the body in Laplace transform form. Now, with the help of Newton's law, we'll find out differential equation of the system. One side of this equation will contain all the forces acting in the direction of motion, which is in this case will be externally applied force f of t, and the second side of equation will contain all the forces acting on the body in opposite direction of motion. So now we'll take Laplace transform with zero initial condition, which will convert our time domain relation into a simple algebraic relation. After taking x of s common from the terms involving it and using cross multiplication property, we'll reach to our desired transfer function, which is x of s over f of s. Students, so now we have found a transfer function for a simple translational mechanical system which consists of a mass m, spring k, and a damper rho v. The externally applied force was f of t, and the system was moving in the direction of externally applied force. In figure B, the very same system is represented in block diagram form, where f of s is input and x of s is the output of the system. Dear students, now we will study impedance for mechanical system. If you look at the portion of table we studied in the start of translational mechanical system, which gave us force displacement relations for spring, viscous damper, and mass. If we look at the relation for a spring, force is equal to spring constant k multiplied by displacement x of t. And if we take Laplace transform, force F will be equal to Kx of s. Now for viscous damper, force is equal to viscous damper constant rho v multiplied by rate of change of linear displacement. Now if we take zero initial condition based Laplace transform, the force will be equal to rho v s x of s. Now for mass m, force is equal to mass m multiplied by double derivative of linear displacement. And for this, in Laplace domain, force will be equal to mass m multiplied by s square multiplied by x of s. Now if we look at force displacement relations for spring, viscous damper and mass, we conclude that force is equal to impedance of the mechanical component multiplied by linear displacement. Or we can say that impedance for mechanical system is force divided by linear displacement. Or we can say that sum of applied forces is equal to linear displacement covered by mechanical component multiplied by sum of impedances. Now if any of you have any questions, please ask. Dear students, welcome to the 5th online class of Control System Engineering. In the last class, we studied about operational amplifier and how to find transfer function for two basic configuration of op-amps. The first one was inverting op-amps and second one was non-inverting op-amps. In case of inverting op-amps, as the name implies, output of the system was out of phase with respect to input, whereas in the case of non-inverting operational amplifiers, output of the system was in phase with respect to input. After op-amps, we studied about translational mechanical system, in which we started with passive linear components we are going to use in this topic. The components include spring, mass, and a viscous damper. Among these, spring and mass are energy storage element, whereas viscous damper is a energy dissipating element. We studied their force velocity relation and force displacement relation. Afterwards, we started how to find transfer function for a simple translational mechanical system. There are certain rules were defined which we are going to follow step by step for transfer function. And finally, we concluded our last lecture with the topic of impedance for mechanical system, in which we observe the force displacement relation for a spring, viscous damper and mass, and concluded that impedance for mechanical system is equal to force divided by displacement, or sum of applied forces is a product of sum of impedances multiplied by the linear displacement. This is all about lecture 4. Now we'll start lecture 5. Students, by the end of this lecture, you will be able to find transfer function for a linear time invariant translational mechanical system, whether the system is a simple or a complex. Dear students, in this lecture, we will start from translational mechanical system and then we will start rotational mechanical systems, and we'll study how to find transfer function for them. Dear students, in previous lecture we studied how to find transfer function for simple translational mechanical system. Now we will study how to find transfer function for complex translational mechanical system. The complex translational mechanical system are just like complex electrical networks, which depends on multiple loop or multiple node circuit. For this system, we have more than one differential equation to describe the dynamics of the system. And these number of equation depends on degree of freedom of a system or linear independent motion. Here linear independence means that a point of a system which can move if all other points of the system are held still. The number of points define degree of freedom and is equal to the number of equation required to describe the dynamics of a system. Dear students, now we will study how to find transfer function for complex translational mechanical system. As there were certain rules for electrical network analysis, here again we have certain set of rules which we are going to follow to find transfer function. For any given system, first of all we will find degree of freedom, or we have to identify how many linear independent motion exist in a system. This will define number of equations required to define dynamics of a system. After defining number of equations, we will draw free body diagram for each point of motion. Now after drawing free body diagram, we will define direction of motion. In what direction that point of motion is going to move. After defining the direction, we'll use superposition principle. In superposition principle, we'll place all the forces acting on a body, either due to its own motion or the motion of other point of motion. These forces acting on the body can either be in the direction of motion or direction opposite in which object is moving. Students, now after finding forces acting on each free body diagram, we'll make an equation. One side of equation will contain sum of forces acting in the direction of motion, where second side of equation will contain forces acting in opposite direction. After this, we'll solve the simultaneous set of equations and find our required transfer function. Dear students, now with the help of example, we'll study how to find transfer function of a mechanical system. In this example, you have to find transfer function x2 of s over f of s. If we look at the figure, in this system we have two masses m1 and m2. m1 is moving in the direction of x1, where m2 is moving in the direction of x2, which means that their direction is already defined. The externally up force F of t is acting on object m of 1. m1 is attached with k1, M2 is attached with K3. The components common between M1 and M2 are a damper with coefficient rho v3, a spring with a constant K2. Both M1 and M2 are experiencing surface friction, which are represented by rho v1 and rho v2 respectively. We'll find the relation of x2 of s over f of s, which means with this transfer function we can find what linear displacement will be covered by M2 when an externally applied force f of t will act on M1. Dear students, now we'll start the solution. With the help of rules defined earlier, the first rule was to define the degree of freedom. As from the figure it is clear that degree of freedom is equal to 2 because each individual mass M1 or M2 can be moved on the horizontal surface if second one is held still. If you hold still M2, M1 can move easily, or if you hold still M1, M2 can also move freely. Now in step 2, for each masses which can move freely, we'll draw free body diagram and define the direction of motion for each mass M1 and M2. In step 4, we'll use superposition principle to identify what forces are acting on either M1 or M2 and in what direction every single force is acting on these objects. Like for M1, forces will act either due to the motion of M1 or can be transmitted through the system or components attached between M1 and M2 if M2 is moving where M1 is hold still. Basically, we are trying to identify what forces are acting on M1 in what direction in case M1 is moving or it is held still. After superposition principle, we will apply Newton's law on each free body diagram to find out equations of motion. We will perform Laplace transform with zero initial condition and then we will find out our desired transfer function by solving this equation. Dear students, now we will analyze free body diagram for mass M1. Now if you look at the figure of translational mechanical system, in this we have object represented by mass M1 which is moving in the direction of x1 of t. The externally applied force is F of t. The mechanical components attached to M1 are a spring with coefficient K1. There is another spring with coefficient K2. We have a viscous damper represented by rho v3. Both K2 and rho v3 are common between M1 and M2. The surface friction of M1 is represented by rho v1. Now we will apply superposition principle to identify how many forces and in which direction are acting on M1. For this, if you look at the top figure, we have 3 sub-diagrams. If you look at the figure A, which represents forces acting on the body M1 when m1 is moving and m2 is hold still. When m1 will be moving in the direction of x1, spring with coefficient k1 will apply an opposing force. Spring with coefficient k2 will also oppose its motion. Surface friction represented by coefficient rho v1 will also oppose its motion. The viscous damper common between m1 and m2 represented by coefficient rho v3 will also oppose its motion, and its mass will also oppose the motion. The only force which will be acting in the direction of x1 will be externally applied force F of t. Now in figure B, we are going to identify how many forces and in which direction they are acting on m1 when m2 is moving in the direction of x2 and m1 is held still. When m2 will be moving in the direction of x2, the components common between m1 and m2 are a viscous damper with coefficient rho v3 and a spring with coefficient k2. When m2 will start its motion, the spring k2 and viscous damper rho v3 will oppose the motion of m2, but as other end of these both component is attached to m1, so they will also try to move, or m1 will experience a force which will be acting in the direction of x2. x1 and x2 both have the same direction, so m1 will experience a force in the direction of x1. Now in third subfigure, we have placed all the forces of subfigure A and B on a single free body diagram, and these are all the forces which are acting on m1 either due to its own motion. Dear students, now we'll apply a superposition principle on m2 to find out how many and in what direction forces are acting on the object. If you look at the original system diagram, the components attached with m2 are a spring with coefficient k3, surface friction represented by coefficient rho v2, a viscous damper with coefficient rho v3, and a spring with coefficient k2 are common between m1 and m2. Now we'll apply superposition principle. Now if you look at figure A shows all the forces experienced by m2 when m1 is stationary and m2 is moving in the direction of x2. The spring with coefficient k3 applies an opposing force. The surface friction represented by rho v2 applies an opposing force. Both spring and damper common between m1 and m2 applies an opposing force on m2. The mass of m2 also applies an opposing force on m2. Now if you look at figure B shows all the forces acting on or experienced by m2 when m1 is moving and m2 is held stationary. In this scenario, the components common between m1 and m2 applies a force in the direction of x2. So k2 x1 of s and rho v3 s x1 of s will be in the direction of x2. In figure C, we have summed all the forces acting on M2. Dear students, in next step, we'll form the equation of motion. One side of equation will contain sum of all the forces acting in the direction of motion, and another side will contain all the forces acting in direction opposite to the motion. And we will repeat this process for each free body diagram. And hence, with little rearrangement, we'll obtain our desired equations of motion. We will solve these equations and our desired transfer function, which is x2 of s over f of s. Here again, every student have choice to choose which method suits him. In this example, we have used Cramer rule, and our desired transfer function is x2 of s over f of s equals rho v3 s plus k2 divided by del, where del is defined below. This transfer function can be represented in a form of a system whose input is force F and output is x2 of s, where transfer function is represented by g of s. It means that we can study behavior of any translational mechanical system, or we can find out what linear displacement will be covered when force F of s is applied. Dear students, now we'll make generalized equation for inspection method for a system whose degree of freedom equals 2. If we compare equation from last example with given translational mechanical system, the system consists of two masses, and the first equation is for mass m1. The first part of this equation contains sum of impedances which are directly connected to the motion of x1 multiplied by x1 multiplied by x1 of s, subtracting sum of impedances between x1 and x2 multiplied by x2 of s, and this equation will be equal to sum of externally applied forces at x1. Now, second equation is for m2 and is made up of sum of impedances which are connected to the motion of x2 multiplied by x2 of s, subtracting sum of all those impedances which are common between x1 and x2 multiplied by x1 of s, and this will be equal to sum of applied forces at x2. You can also compare this generalized form with given set of equations, and this generalized form will be used for inspection method for a system with degree of. Dear students, next example is also based on equations of motion by inspection method. In this problem, we have to find only equations of motion for a given mechanical network. We'll start the solution of system by finding degree of freedom. If you see, in this system we have three masses which can perform linear independent motion, which means that m1 can move freely if m2 and m3 are held stationary. Likewise, m2 can move freely if m1 and m3 are held stationary. Similarly, m3 can also move if m1 and m2 are held stationary. So by this system has a degree of freedom 3 and we'll find three simultaneous equations of motion with the help of inspection method as required in problem. Dear students, now we will study how these generic equations are formed. For first object, mass m1, equation will be like sum of impedances connected to the motion of x1 multiplied by its linear displacement, which is x1 of s, minus sum of impedances common between x1 and x2 motion multiplied by motion of the second point, which is x2 of s minus 2 of s, minus sum of impedances which are common between motion of x1 and x3 multiplied by motion of third point, which is x3 of s, and this equation will equal to sum of applied forces at x1. This will give us first equation. For second equation, we'll start from sum of impedances connected to the motion of x2 multiplied by motion of second point, which is x2 of s, minus sum of impedances common between x1 and x2 multiplied by motion of first point, which is x1 of s, minus sum of impedances between x2 and x3 multiplied by x3 of s, and this will be equal to sum of applied forces or any external force acting at point x2. Now last equation will be like sum of impedances connected to the motion of x3 multiplied by motion of third point, which is x3 of s, minus sum of impedances common between x2 and x3 multiplied by motion of second point, which is x2 of s, minus sum of impedances between x1 and x3 multiplied by motion of first point, which is x1 of s, and this will be equal to sum of applied forces at x3. Dear students, now using the generic form of inspection method studied in previous slide, we'll use for current example, and we'll find out or write our required system of equation in this case. Here we have three equations defining dynamics of a system in Laplace domain. First equation is for our test point or mass m1. Second equation is for mass m2, and the last equation is for mass m3. Dear students, now we will start rotational mechanical system, in which we will study about components used and how we will find a transfer function for a rotational mechanical system. Again, in this system, the passive linear components used are spring, inertia, and viscous damper. Spring and inertia are energy storage element, whereas viscous damper is an energy dissipating element. The analysis of rotational mechanical system is quite similar to translational mechanical system. The only difference is, in this, forces are replaced by torques, because in this rotational motion is performed is performed instead of linear motion. Here is a table for passive linear components like spring, viscous damper, and inertia, and this table defines torque to angular velocity relation for spring, viscous damper, and inertia, torque to angular displacement relation for spring, viscous damper, and inertia, and in last column we have impedance for spring, viscous damper, and inertia. Dear students, after studying passive linear components used in rotational mechanical system, now we will start how to find transfer function made up of these components. As said earlier, the rules for rotational mechanical system are quite similar to that of translational mechanical system. We will start from defining degrees of freedom or linear independent motion. In this, we will find out how many points exist in a system which can rotate freely. And these will be our test points. And will define number of equations required to define the dynamics of a system. After defining degrees of freedom, we will make free body diagram for each test point of the system. After free body diagram, we will define direction of rotation of each test point. The direction will be either clockwise or anti-clockwise. After defining direction of rotation, we will use superposition principle to find out how many and in what direction torques are acting on our test points. For this, we will begin by holding all the test points of rotation still and will find out how many torques are acting on the body due to its own motion. Then we will hold the body and activate all other test points of rotation one at a time and placing on original body all the torques acting due to adjacent rotation. Dear students, after applying superposition principle on every test point, we will find system of equation by summing the torques acting either in the direction of motion or opposite to the direction of motion for every test point. This will give us a simultaneous equations of the system, and we will solve these equations for our required transfer function. Students, now with the help of example, we will study how to find transfer function of a rotational mechanical system. In this example, you have to find transfer function theta 2 of s over t of s. We will start the solution by finding degree of freedom of this system. This rotational mechanical system consists of a viscous damper with coefficient d1, inertia with coefficient j1, a spring with coefficient k, another inertia with coefficient j2, and a viscous damper d2. If we look at arrangement of components in system, one end of d1 and d2 is tied to a fixed wall, so they can't rotate freely, where j1 and j2 are such a point of system which can rotate freely. So this system has a degree of freedom equals 2. Now we'll find equation of motion by following given set. Students, solution starts by finding degree of freedom for a system. In last slide, we have already identified that for this system, degree of freedom equals 2. After degree of freedom, we will draw free body diagram for each test point. Then afterwards, we will define direction of rotation for each test point. After step 3, we will apply superposition principle on every test point of the system. With superposition principle, we will find out that how many torques and in what direction they are acting on a test point. For example, consider test point theta 1. Torques acting on the theta 1 are due to its own rotation and due to the rotation of theta 2, which are transmitted to theta 1 through the system. Then we will sum the torques for equation of motion. Dear students, in this slide we will study free body diagram for first test point J1. If you look at the figure of the rotational mechanical system, J1 is attached to a viscous damper D1 and a spring K. And externally torque is applied on a point theta 1. Now if J1 rotates in the direction of theta 1, the viscous damper attached to it will oppose its motion. Spring with coefficient K will also oppose its motion, and its own inertia will again oppose its motion. And the externally applied torque will act in the direction of rotation. If you look at figure A, all the torques are presented in Laplace domain. Torque due to spring, viscous damper and its own inertia are represented with the arrow in opposite direction to the theta 1. In case of figure A, it is assumed that second test point is held stationary. Now in case of figure B, it is assumed that first test point theta 1 is held stationary, where second test point theta 2 is rotating. The common component between J1 and J2 is spring with coefficient K. When theta 2 will rotate, the spring K attached to it will oppose its motion. But if we see, the second end of spring is attached to inertia J1, so it will tend to rotate J1 in the direction of theta 2. And due to this, our torque will be experienced by theta 1 transmitted through the system. And as both direction of theta 1 and theta 2 are same, so J1 will experience a torque in the direction of theta 1. Figure C is the final diagram in which all the torques acting on J1 are represented, either in the direction of rotation or opposite to the direction of rotation, which is theta 1. Students, now we will analyze free body diagram for our second test point J2 for the equation of motion. If you look at the diagram of rotational mechanical system, in this, inertia J2 is attached to a spring with coefficient K and a viscous damper with coefficient D2. When J2 will rotate in the direction of theta 2, spring attached to it and viscous damper both will oppose its rotation and apply a torque in opposite direction. Similarly, in the case of inertia, it will also oppose the rotation. Now look at figure A. In this, J2 represent our second test point, theta 2 is direction of rotation. Torques acting in the opposite direction are torque due to inertia, torque due to spring, and torque due to viscous damper. For figure A, it is assumed that first test point is stationary, which means theta 1 of s is equal to 0. Now consider second case. In this it is assumed that theta 1 is rotating in the direction of applied torque, where theta 2 is held stationary. Due to this rotation, J2 will experience a torque in the direction of theta 1, which is transmitted with the help of spring K, and will be equal to K theta 1 of S. Figure C represents all the torques acting on test point J2. Dear students, now for the equation of motion. Each equation will be found out by summing all the torques on that respective free body diagram. After summing and rearranging, we will get two equations of motion. First equation is associated with first test point, where second equation is associated with our second test point. Now the desired transfer function can be found with any appropriate method. Here we have used again Cramer rule. So theta 2 of s over applied torque will be equal to K over del, where del is defined here. This system can be represented in a block diagram form, whose input is externally applied torque T and output is angular displacement covered by the system, where transfer function is represented by K over del, and delta have a predefined form given in the slide. Now if any of you have any questions, please ask.